So our big picture goal this week is to make sure that you have all the tools you need to successfully predict the shape of an EDTA titration curve and predict the amount of free metal ion that will remain in solution after any given amount of EDTA added. Our focus today will be on using formation constants to calculate the amount of metal ion that remains in solution at any given EDTA concentration. A formation constant, also known as a stability constant, or K sub f, is just another class of equilibrium constant that describes the extent of reaction between a metal ion and a ligand, a Lewis base with an electron pair that donates to form a bond with the metal ion. So if we use our abbreviation for EDTA, our standard EDTA abbreviation of Y4- for the fully deprotonated EDTA, our generic equation to describe the chelation of a metal ion by EDTA is Mn plus Y4- forms the complex MyN4-. This is an equilibrium reaction where Mn plus is just a generic metal cation with a charge of positive N, and then MyN-4 is our EDTA metal complex. Like any equilibrium constant, or like any equilibrium chemical reaction, we can describe this with an equilibrium constant of the usual form, with products in the numerator, reactants in the denominator, everything raised to their stoichiometric coefficient. EDTA, of course, always reacts 1-to-1 with metals. So the form of our equilibrium constant expression is going to be concentration of the EDTA metal complex in the numerator divided by the concentration of the free metal ion times the concentration of EDTA generally. But as we're going to show, one key plank in our platform here is going to say how we go from EDTA generally should be in the denominator, and in the denominator we have the concentration of the free metal ion and the deprotonated EDTA Y4-. Note that formation constants are written for the Y4- species of EDTA, the fully deprotonated form which interacts most strongly with metals. So we would know how to use an equilibrium constant to calculate the amount of free metal that remains after complexation with EDTA. All we need to know is the value of the formation constant and the equilibrium concentration of the EDTA metal complex. One problem here, though, is that in the denominator, we have the Y4- species of EDTA specifically, but EDTA is a hexaprotic acid and can exist in various deprotonated forms depending on the pH of the solution. So the key skill we want to pick up today is we're going to show you how to construct a conditional formation constant that allows us to relate the total EDTA concentration to the concentration of the Y4- species specifically. Now, one of the first things we'll need is a value for these formation constants. So the value of the formation constant has been indexed for almost every metal on the periodic table, and you can find a table for this in your Harris textbook. This particular version of the table is from an old edition where the EDTA complexation chapter was chapter 13, but you should still be able to find the same table in chapter 12 in the current 9th edition, and it should still be table 12.1. So the way the table is interpreted, of course, is in the left-hand column of each main column, you have the ion that you're interested in chelating with EDTA. So notice that for +1 ions, the value of the formation constant is quite small. For every other element on the periodic table that forms an ion with a +2 or +3 charge, the value of that equilibrium constant is substantial. The formation constant value is indexed as the log of the formation constant. So if you're interested in calcium ion being complexed with EDTA, which we will be shortly, the value of the base 10 log of the formation constant is 10.65, which means that the actual equilibrium constant of formation for calcium reacting with EDTA is equal to 10 to the 10.65. And so that requires a little extra math and a little extra thought to actually unravel the value of your equilibrium constant, but you can absolutely do it. So just keep that in mind. Make sure you recognize what the table's saying to you. all the formation constants you need for complexing with your standard metal cations can be found here in this table in Harris. All right, but the problem is that at different pHs, different amounts of EDTA will be in the deprotonated Y4- form. And remember that the Y4- form doesn't actually become the dominant form of EDTA until shortly after pH 10. So when we are talking about EDTA complexing with a metal, we don't use the formation constant directly, Kf. Instead, we use what's known as the conditional formation constant, K'F. And K'F is an adjusted equilibrium constant value which takes into account how much of the formal EDTA concentration, so how much of the total concentration of all the species of deprotonated EDTA is in the Y4- form. The conditional formation constant K'F is equal to the alpha value, the fractional composition value of Y4- compared to all the other EDTA species, times the formation constant that you get from table 12.1 in Harris. And so what that's saying then is that your conditional formation constant is equal to the concentration of the metal EDTA complex in the numerator times the free metal concentration in the denominator times the formal concentration of EDTA compared to the fraction of EDTA which is actually in the deprotonated Y4- form. And so the way you calculate conditional formation constant is to get your Kf value from table 12.1 in Harris and get your alpha value for the Y4- form from table 12.3 in Harris, which shows you the different values of alpha for EDTA depending on the pH. So for instance, if you're interested in an EDTA titration that's buffered to pH 10, you come to table 12.3 and you scroll over and you say, well, I'm interested in pH 10. The alpha value is 0.30. And if I want to calculate the conditional formation constant, it's going to be the alpha value 0.30 times the formation constant itself for the metal. And that's all there is to the conditional formation constant. It's just a way of accounting for the fact that not all of your total EDTA concentration will be in the Y4- form. So we use the alpha value times the formation constant value to take that into account.